the problem is that there we are working away in Nottingham on these sophisticated reactors, but our colleagues in Ethiopia at this time don't have such equipment. So the question is, how can we give them access to this equipment? And we've come up with an idea which we call cloud chemistry, rather like cloud computing. And the idea is that many of the reactions that I'm describing make well-known chemicals. So people doing the experiments don't actually need the physical chemical that's produced by the reactor, they just need the analysis. They want to know how well the particular reaction is done. So we came up with the idea, why don't you operate a reactor from a distance using the internet? So you just get the results without the chemical. And this is where it becomes particularly useful that our university has a campus in China, because we wondered whether we could run experiments at Nottingham but controlled from our Chinese campus. And very conveniently, one of my former PhD students, Zhou Wang, is now a lecturer in Ningbo, so he can operate the reactor from a distance. And so here's Zhou in Nottingham with me and with our reactor behind, discussing the experiments. And this is the first reaction that we did. For those of you chemists, reacting isopropanol to make N-propanol to make N-propyl ether. And this is what Zhou saw on his computer. And you can see here is the yield of the product as the reactor optimizes itself. And it got to 25%, which is what you would expect the maximum yield to be for this reaction. And he did this while he was sitting in Ningbo, and we were, my students obviously had to put the chemicals in the reactor, but after that they didn't touch the experiments at all. So the advantage of cloud chemistry is that you can have access to a reactor from anywhere, and you can network labs across the world. So not every lab has to have the same equipment. And particularly it will empower green chemists across Africa, and will bring researchers across the world closer together. So finally, I've got to point out that chemistry buildings, wherever they are in universities, are usually the most energy-intensive building on a university campus. They have fume hoods that are pumping out air from the labs. In Hong Kong, where you have air conditioning, you're pumping out valuable cold air outside through your fume cupboards. In Nottingham, it's hot air because it's a colder country. So we're now partnering with GlaxoSmithKline at Nottingham to build the first chemistry building in the world, which is going to be, or we hope, carbon neutral over its lifetime. And here's a picture of the building. We're just about to start building it, and I won't go through all the features, but some of them are quite unusual. First of all, a lot of the carbon dioxide generated in making a building comes from the concrete, so most of the building is going to be made from wood. And it has solar panels to generate electricity. It has this thing here, which is called a winter garden, which is a greenhouse to catch the sunlight in winter to warm the air. And then it has these chimneys, rather like a big ocean liner, which will produce some ventilation without electricity. And then there are more exotic things, like the insulation in the roof is going to come from the wool from sheep that are from farms around Nottingham, so you don't have the transport cost. And at the moment, farmers can't sell their wool because nobody wants wool much now. So it can be used for insulating the roof. And the roof itself is going to be covered with plants, but special plants that don't grow very big, so you don't need to cut them. And inside, the labs are going to be very high. And the aim is to use 75% less energy. And you can see the lab is shown as empty, because the real challenge is going to be to re-engineer lab equipment so it uses less energy. At the moment, nobody cares when they build spectrometers and things like that. They don't worry about energy usage. So we're working with companies to try and bring this energy usage down. So